In the vast expanse of the cosmos, mysteries abound that challenge our understanding of the universe's origins. The Big Bang theory has long stood as the cornerstone of cosmology, explaining how the universe burst into existence from a singular, dense point. Yet, recent observations by the James Webb Space Telescope, JWST, are shaking the foundations of this well-established theory, suggesting that the cosmos may be far more complex and enigmatic than previously imagined. This narrative delves into the profound discoveries of the JWST, the scientific theories it challenges, and the potential paradigm shift that could revolutionize our understanding of the universe. The Big Bang theory describes the universe's inception as a dense collection of particles that exploded, leading to the formation of stars, planets, and life. Initially, the universe was smaller than the head of a pin before expanding rapidly. This theory, proposed in the early 20th century, revolutionized our understanding of cosmology. It provided a comprehensive explanation for the observable universe's expansion, as first noted by Edwin Hubble in 1929, who observed that distant galaxies were moving away from us, implying a common starting point. According to the Big Bang theory, approximately 13.8 billion years ago, the universe was in an extremely hot and dense state and began to expand. Within the first few minutes, nucleosynthesis occurred, forming the first atomic nuclei. This period was followed by the formation of neutral atoms approximately 400,000 years later, allowing light to travel freely through space. This era, known as recombination, led to the cosmic microwave background, CMB, radiation, a faint glow observable in every direction, providing critical evidence for the Big Bang theory. To study these early moments and the formation of the first galaxies, astronomers have long sought more advanced tools. The Hubble Space Telescope, launched in 1990, provided unprecedented views of the cosmos, including the iconic Hubble Deep Field image, which revealed thousands of galaxies in a tiny patch of sky. However, its capabilities were limited to the visible and ultraviolet spectrum, prompting the need for a more advanced observatory. The James Webb Space Telescope, JWST, launched by NASA, is the largest and most advanced space observatory designed to study the earliest eras of the universe. Named after James E. Webb, the NASA administrator who led the Apollo program, the JWST was envisioned to answer fundamental questions about the cosmos. Development of the JWST began in the mid-1990s, with the goal of observing in the infrared region, allowing it to peer further back in time than Hubble. The JWST's infrared capabilities are crucial because as the universe expands, light from distant objects is redshifted, stretching into longer, redder wavelengths. By observing in the infrared, the JWST can detect this redshifted light, revealing objects and events from the universe's infancy. The telescope's primary mirror, composed of 18 hexagonal segments, is over 6.5 meters in diameter, significantly larger than Hubble's 2.4-meter mirror, allowing it to collect more light and see fainter objects. After decades of development and a cost of approximately $10 billion, the JWST finally launched on Christmas Day 2021. Following a month-long journey to its destination at the second Lagrange point, L2, about 1.5 million kilometers from Earth, the telescope underwent extensive testing before it was ready to begin its much-anticipated first year of science observations, known as Cycle 1. One of the most remarkable discoveries came early in the JWST's mission. Astronomer Rohan Naidu discovered an ancient galaxy, Glass Z13, which dates back to just after the Big Bang, challenging existing models. This galaxy appeared mysteriously gigantic and unexpectedly well-developed for its age. Naidu's excitement was palpable as he shared the revelation with his colleagues, describing it as more than astronomers could imagine. This galaxy, along with others detected by the JWST, appeared to be far more massive and mature than models of early galaxy formation had predicted. JWST's findings revealed unexpectedly bright and massive galaxies, some with redshifts estimated at 20, indicating their formation shortly after the Big Bang. These galaxies showed disk-like structures that were not expected for such early cosmic ages. Additionally, another team found evidence for smooth spiral galaxies at a redshift of 10, less than 500 million years after the Big Bang. The rapid formation of these large galaxies contradicts the lambda cold dark matter, lambda CDM, cosmological model, which posits that galaxy formation should be a gradual process influenced by the slow accumulation of dark matter. The lambda CDM model has been the prevailing cosmological paradigm for decades. It describes a universe composed of ordinary matter, and dark energy, with dark matter playing a critical role in the formation and evolution of cosmic structures. According to this model, dark matter provides the gravitational scaffolding around which galaxies form, while dark energy drives the accelerated expansion of the universe. However, the JWST's discoveries suggest that the early universe may have been more dynamic and complex than the lambda CDM model accounts for. The rapid formation of large galaxies challenges the expectation that galaxy formation should be a slow, hierarchical process. This discrepancy raises important questions about the nature of dark matter, the processes driving galaxy formation, and the overall timeline of cosmic evolution. Follow-up observations from the Atacama Large Millimeter Array, ALMA, in Chile did not detect significant amounts of dust associated with glass C13, complicating mass calculations. Dust is a critical component in star formation and galaxy evolution, as it absorbs and re-emits light, influencing observations. The absence of dust in these early galaxies suggests that our understanding of their formation and evolution may need revisiting. The unexpected discoveries suggest that the standard cosmological model may need updating. One controversial proposal is to modify Newtonian dynamics, questioning the existence of dark matter. The modified Newtonian dynamics (MOND) theory, proposed by Mordechai Milgrom in the 1980s, suggests that the observed discrepancies in galaxy rotation curves and other phenomena attributed to dark matter could instead be explained by altering the laws of gravity at low accelerations. Although MOND has had limited acceptance among cosmologists, the JWST's observations may lend some support to the theory. If the rapid formation of large galaxies in the early universe cannot be reconciled with the lambda CDM model, alternative explanations such as MOND might gain more consideration. However, not all cosmologists are convinced of the validity of MOND, and further observations and theoretical work are needed to explore this possibility. Another possible explanation is that early galaxies in the universe may have had very little dust, making them brighter and affecting mass calculations. This scenario could explain why the JWST detected such bright and massive galaxies so early in cosmic history. If star-forming conditions in the early universe were more efficient, leading to the rapid formation of high-mass stars, it could account for the observed discrepancies. David Spergel, a prominent astrophysicist, supports this idea, suggesting that the conditions for star formation may have been different in the early universe, leading to more rapid galaxy growth. The JWST's discoveries offer a glimpse into the universe's past, prompting new questions about the early stages of cosmic evolution. Continued observations and research are essential to reconcile these findings with existing models. As scientists continue to dissect the JWST data, the implications of these revelations could be profound, ushering in a new era of cosmological understanding. The surprising discoveries of this remarkable observatory offer a fascinating glimpse into the past of the universe, encouraging humanity to try to unravel the mysteries of existence. As early systems came into being, researchers and viewers alike found themselves struggling to understand them. Could this cluster of unexpectedly large and bright early galaxies be the result of errors in the telescope's analysis of the original observations? Or, if they are genuine, can they somehow be reconciled with standard cosmological models? It's possible that the universe is stranger and more complex than our wildest speculations allow. At stake is nothing less than our understanding of how precisely the universe, as we know it, emerged from primordial chaos. The first findings of the James Webb Space Telescope can rewrite the early chapters of cosmic history. These numbers concern not only distant ages and distant galaxies but also our own existence in the Milky Way. As Mark McCaffrian, the European Space Agency's senior science and research advisor on JWST, commented, "You don't build these machines to reinforce a worldview, you build them to break it. You just don't know how it's going to break." In some ways, JWST observations of early galaxies have been made for billions of years, but more subtly, they originate from the Space Telescope Science Institute in 1985. At the time, The Hubble Space Telescope was still 5 years away from launch, but the director of the institute at the time, Riccardo Giacconi, asked his team to think about what may come after Hubble in the much more distant future. Despite his focus on Hubble's successor, Giacconi was persistent and predicted a long development process. Garth Illingworth, then deputy director of STSCI, began to develop ideas with a small team for what would later become the Next Generation Space Telescope, NGST, later renamed JWST. They realized that although Hubble was groundbreaking, its capabilities